In this video for section 3.2, we will look at the mean value theorem. The mean value theorem has a significant purpose in our study of applications of differentiation because the mean value theorem is going to enable us to obtain information about a function from information about its derivative. So because of the mean value theorem, what we'll be able to do is determine some factors of a function's graph by looking at a function's derivative. So let's get started on the mean value theorem. To jump off to the mean value theorem, the first thing we need to do is start from another theorem, which is called Rolle's theorem. It's important to note that if you see the title of this section, it's the mean value theorem. The mean value theorem really is the significance of 3.2. But to get the mean value theorem, we have to take an intermediate step into Rolle's theorem. Rolle's theorem is what the mean value theorem will rest. So let's start with an introduction to Rolle's. Here's the theorem. We have a hypothesis and we have a conclusion. It's an if-then statement. So if the hypothesis is true, then the theorem gives us conclusion is true. So the hypothesis is the if statement. If f is a function that satisfies the following three hypotheses, so here's the hypothesis. The function is continuous on the interval AB. The function f is differentiable on the open interval AB, and at these two endpoints A and B, the value of the function is equivalent. So f of A is equivalent to B. Those are the three hypotheses. The function's continuous and differentiable on this interval, and at the endpoints f of A and f of B, the value is equivalent. So if we have these three hypotheses met, then here's what we can conclude. We can know that there's a number C somewhere in between A and B such that the first derivative of B is equal to 0. Let's look at an example of that. And if you'd like this page along from, you could print this page from Blackboard. So this page, this worksheet, is available on Blackboard to use to follow along with. So again, 3.2, the main significance of the mean value theorem is that it enables us to obtain information about a function from information about a derivative. And Rolle's theorem's purpose is going to be that it's going to help us prove the mean value theorem. So let's stop and take a look at the Rolle's theorem. Here's an example applying Rolle's theorem. The question would read, verify that the function satisfies the three hypotheses of Rolle's theorem. And then once you've verified that it meets the hypotheses, find all the C's, so all the numbers on this interval from 0 to 3, that satisfy the conclusion. So first of all, is f of x continuous on the closed interval? The answer is yes. It's continuous. Why? Because it's a polynomial. In an earlier chapter, we had this theorem that if a function was continuous, if it's a polynomial, then it is continuous. So because this is a polynomial, we know that it's continuous. Furthermore, because it's a polynomial, we know that the function is differentiable as well. So we can meet these two pieces of the hypothesis. Now we need to show, is it true that at these two endpoints the value of the function is equivalent? This is easily done with some algebra. We're going to replace the x with 0 and get 0 minus 0 minus 0 plus 2 equals 2. And then replace the x with 3. 3 cubed minus 3 squared minus 6 times 3 plus 2. That's 27 minus 9 minus 18 plus 2. Well, 18 plus 9 is 27, so I know that this simplifies to 0. Plus 2 is 2. So yes, f of 0 is in fact equal to f of 3. So we can check all three of the hypotheses out. We have verified that this function meets the hypotheses of Rolle's theorem. Because the function meets the hypotheses, the function's continuous, differentiable, and the value of f of 0 was equal to the value of f of 3, we know that there's a number c somewhere between 0 and 3, such that the first derivative is 0. And what we need to do now, our question asks us to find all those c's. So let's start by finding the derivative. The derivative is 3x squared minus 2x minus 6. And if we set this derivative equal to 0, I could factor this or will it factor? You know, I don't think this is going to, because we have a 3 and a 2 or a 2 and a 3. We're getting 9 or 3 and 6 or 9 and 2. It looks like this one's not going to factor. So because it doesn't factor, it doesn't mean I can't solve it. It just means that to solve, I've got to go a different direction and I'm going to try the quadratic formula. X equals the opposite of b plus or minus the square root, b squared minus 4ac all over 2a. Minus 4 times negative 3 times negative 6 would give us positive 72. All over 2 times 3, so all over 6. And this will simplify to 1/3 plus or minus the square root of 19 over 3. If I estimated this, if I could get an approximation and say that this is approximately 1.79 or negative 1.12. But these are the two C values. These are the two C values that satisfy the conclusion. So therefore, C equal to 1/3 plus or minus the square root. Satisfy the conclusion of Rolle's theorem. So there's an example using Rolle's theorem. Let's get to the real meat of this section, the mean value theorem. So once we have Rolle's theorem, we're able to use it to prove and then be able to use the mean value theorem. So let's look at the mean value theorem. The hypothesis is if f is a function that is continuous on the closed interval AB and differentiable on the open interval AB, then the conclusion is that there's a number c somewhere on the interval ab such that the first derivative at c is equal to the slope of the line that we draw between those two endpoints from A to B. Notice that this f of B minus f of A, say, this is what we would describe as the slope of the secant line. F of B minus f of A over B minus A. This is the slope of the line from A, f of A, to B, f of B. So given these two x's and two y's, the slope between those two endpoints that we had, our A and our B, is going to be equivalent to the derivative. Or equivalently, if we put this in point slope form, we'd have f of B minus f of A equals f prime of C times B minus A. And again, let me remind you again the purpose of the mean value theorem. It's going to enable information about a function by using its derivative. Let's look at a few graphs of some functions that satisfy the hypotheses of the mean value theorem. So here we have a constant function. Constant function is continuous and differentiable from A to B. And then we have another function that from A to B, it's continuous and differentiable. Two more. All four of these green functions are continuous and differentiable from A to B. So what we can say from this mean value theorem is that somewhere on the graph there's a C such that the first derivative is equal to the slope of the line we'd get if we connected A and B. This one's easy because the slope is just 0. And somewhere on this function, actually since it's a constant function, it ends up being every C, every value from A to B. The derivative is 0. So it's the mean value theorem is satisfied with every C. Let's look at this next example. Example B. If I were to pick the two endpoints, A and B, and find of the line that connects them, so I'll start by drawing that line, we find that once again, the slope between those 2 points is 0. And is there a point C somewhere between A and B such that the derivative is 0? Sure, it's right here. We get a point, and so our C falls between A and B. And so you see that from the mean value theorem, we knew that somewhere there was going to be a point that did that. If we looked at this example from A to B, somewhere on this graph there's a point C with the same derivative, which was equal to 0. And that case C actually has 2 examples. But that's the mean value theorem. Let's look at some that aren't as boring, have a derivative other than 0. So we can see here's our function, the green function, and here's our point A and B. If I draw a line and then examine the slope, do you see just even geometrically, if I'm looking for a line that's tangent to this parabola somewhere, do you see that I can find a point where the derivative, so the line tangent that point, is parallel to my pink line? Here it is. So again, here's the line we're trying to match up to. We're trying to find a tangent line to this function that's line is parallel to our, so in other words, it has the same slope. And as I look at the different tangent lines to this green function, I find that right here I get something with an equivalent slope, or something that's parallel to the pink line. Over here, if we connect A and B, you see if I followed this function along. I'd get, at this point P, the line that's tangent to the function is parallel to the pink line. If I kept going, I find that it happens again down here. But what the mean value theorem gives us is that somewhere between A and B, you'll find a point whose derivative is equal to the slope of between A and B. That's the mean value. Let's look at an example from the homework that applies the mean value theorem. Here's the theorem one more time. And here's the question. Verify that the functions have 3 hypotheses of the mean value theorem, and then find all the numbers that satisfy the conclusion. So all the numbers such that the derivative is equal to the slope of the secant line. So here's the work with, x cubed minus 3x plus 2. It's a polynomial, so we know that it is continuous and it is differentiable. How do we know that? We can say because it's a polynomial. So what we next need to do is show that there is a number c somewhere on this interval from -2 to 2 such that the first derivative at c is equal to the slope of the point between -2 and +2. So we want to find this point. Let's start by finding the slope of the secant line. Or actually, let me say let's start first by finding the derivative. We get 3x squared minus 3. And we're going to try and find a c. So let's say that f prime of c is 3 squared minus 3. And we want to find f of c such that f of 2 minus f of the opposite of 2 divided by x minus -2 minus 2. We want to find this c. So we've got 3c squared minus 3 equal to f of 2. Off to the side, I could find the value of f of 2. 2 cubed minus 3 times 2 plus 2 equals 4. 8 minus 6 plus 2. F of the opposite of 2, -2 cubed minus 3 times -2 plus 2. So -8 plus 6 plus 2. -2 plus 2 is 0, so 4 minus 0. -2 minus 2 is -4. So we have over -4 or positive 1. I'm sorry, -2. I think I wrote this wrong. It should have been 2 minus -2, so that I kept those in order. So 2 -2 would come out to a positive 4. So this 4 minus 0 over 4 is equal to 1. Now I just need to find c. I'm going to use the square root property. Rather than factoring and setting it to 0 and factoring, I'm just going to use the square root principle. The reason why is we only have a third. We don't have a c term here. So we have 3c squared equals 1 plus 3. C squared equals 4 over 3. So c is going to be positive square root of 4 over 3. Because what I'm doing here is I'm going to take the square root of both sides. using the square root principle. But when you use the square root principle, you have to say that it's plus or minus the square root of 4 over 3. Two C's are 2 over the square root of 3 and negative 2 over the square root of 3. And on our, we've got to go back to our interval that we were going from negative 2 to 2, and both of these do fall in to our domain, our set domain. So they both satisfy the hypothesis of the mean value theorem. So it looks like the C on negative 2 to 2 that fulfills the mean value theorem is C equals 2 over the square root of 3, C equals negative 2 over the square root of 3.